Hello everyone, and good afternoon. I'm Rowen Wu. I'm a product manager at a company called Q-CTRL, and you might notice that there are two faces on that screen, but only one on stage. I will be presenting on behalf of both myself as well as Hiroshi Yamauchi from SoftBank. And SoftBank is the main driver of this case study, and they've graciously allowed me to speak on behalf of some of the very interesting and incredible work that they've done. So just starting off with a bit about the company that I work for, called Q-CTRL. We are a quantum infrastructure software company, and we build software that builds on top of quantum hardware platforms to suppress errors, increasing the usability, the reliability, and the performance of these quantum hardware platforms. We enable users to run circuits with more gates, more qubits, enabling them to achieve peak performance at scale on these quantum hardware platforms. So if you've typically run an algorithm on a quantum device, you'll get this experience where you prepared everything nicely on simulators, you got the right answer, everything was going great, and then you run it on the real hardware, and you find that what you get in response is very noisy results. And this is a common experience across all types of hardware platforms and modalities. And typically, if you want to avoid this type of noise, then you would have to implement specific error suppression and mitigation strategies, or in the future, quantum error correction, to help you to reduce the amount of noise and actually achieve the types of results you got in simulation. And so this can be a very complex process that you have to tailor to every single algorithm and every single use case that you're developing. Instead of doing that, we've built out an automated pipeline that optimally configures your circuit at the gate and pulse level to run at peak performance on the given hardware platform of your choosing. And so this entire process of compiling the circuit, adjusting the pulse shapes, actually tuning the specific layout of the circuit to the qubits on the device, all of this is done by this automated software package called FireOpal. And FireOpal is algorithm and application agnostic, meaning that out of the box, it can be used on any type of application, like the one we'll be talking about, this quantum machine learning use case. And so the benefits of using this type of error suppression extend to being able to run deeper circuits, meaning that you can actually run circuits that are 10 times deeper in terms of the number of 2-qubit gates, meaning you can go from toy problems of not much interest and not much novelty to the types of applications that SoftBank has achieved and published in their paper. In addition, you can actually reduce the overall runtime of your application by reducing the total number of shots that you need to run it and get good results, as well as by eliminating expensive, heavy overhead error mitigation techniques. All of our methods are deterministic. They run one circuit when you run one circuit, and you'll get back good results at the runtime of your initial execution. And then lastly, improved performance is our main prerogative, and we'll definitely demonstrate that in this SoftBank use case. The last thing I'll say about our software specifically is that we have recently launched this software package directly integrated on the IBM Quantum platform. So IBM has offered a new type of package and software called Qiskit Functions. And with this, you can use all of your existing IBM Quantum credentials, your same experience and workflow, and you can simply leverage providers like Q-CTRL to get good performance on the devices without any sort of configuration or additional overhead. Now let's get to the real meat of this, the SoftBank use case. So SoftBank published this paper, as well as they conducted their study earlier this year, and they showed that they were able to achieve great results using a quantum kernel learning technique to diagnose failures in a network telecommunications data set. In telecom, you can imagine that there are vast amounts of data, millions, billions, maybe even this septillion number that we've heard so much about today. Data points that are continuously being aggregated and sent by all of the many devices out there. And SoftBank is one of the biggest providers of telecom in Japan, and meaning that they need to be ensuring the reliability, performance, and security of their systems. So one big challenge is parsing through these large data sets and finding where faults have potentially occurred and then classifying them. So here on the right, you can see kind of the visualization of a network fault classification. And this is an interesting problem that can be solved potentially through machine learning, classically, or potentially you can even use quantum machine learning in order to speed up and make more efficient certain parts of the machine learning workflow. So typically, when you would be doing an implementation of what's called a support vector machine, you would go through this process of preparing your data, of reducing the dimensionality of the data, and you would do essentially what is called a gram matrix calculation. And this part of the workflow, it can become very computationally expensive when you're doing it on extremely large data sets and with extremely high dimensionality. And so this part of the workflow could potentially be offloaded onto a quantum computer. And in this sense, you're taking this classical technique and approach in machine learning, and it becomes a quantum machine learning algorithm where you're using the hybrid combination of classical and quantum computing to together help to resolve the capacity constraints and limitations of classical computing. And then you can go back to continuing to use the benefits of classical computing to actually do the classification process. SoftBank's novel approach is to improve the quantum kernel learning aspect by using something called parameterized circuits. Parameterized circuits allow you to sub in values at runtime, meaning that you can actually make decisions at runtime about what the values of certain parameters in your circuit should be. And this allows for greater efficiency because you can compile a circuit one time and then sub in many values. And it also allows for better accuracy in this case or better efficiency in other cases, where you can basically tailor and tune this parameter to make it optimal for your specific use case. And so by being able to tune this parameter alpha within their circuit, they're able to actually adjust the strength of the quantum entanglement to increase the accuracy of the classification. And so first, SoftBank tested this on using simulation. They first tried out different values of alpha and were able to deduce what values of alpha are going to be optimal for different qubit counts. And then they also ran a comparison using different types of simulation. They compared a traditional quantum support vector machine, or QSVM, to their novel approach, this parameterized QSVM. And then also they compared it to a classical technique, just a classical support vector machine. They saw that their approach does at least as well, if not better, than both the classical technique as well as the traditional quantum SVM. And so this gave them confidence that this is the right way to go. Perhaps this would be an interesting direction to now validate on real hardware. And so next, they moved to validating this on real hardware, both using the FireOpal error suppression package as well as without the FireOpal error suppression package. And they compared these results to two different types of an ideal, one being a tensor network simulator and one being a typical state vector simulator. And so as you can see, the results using error suppression much more closely approximate the actual ideal values achieved using simulation. And you can start to actually push this at greater scale and push this further, all the way up to 50 qubits and potentially even beyond as devices are continuously improving. And so they were able to get confidence that with better devices, using error suppression, they're able to actually achieve good results on their specific use case and good classification accuracy, as well as they were able to know that this methodology will likely scale with these, the improvements in quantum and potentially do better than classical techniques moving forward. So one of my favorite pieces about this example and this case study with SoftBank is that we met the SoftBank team in November of last year, 2023. They started using FireOpal in December, just the next month, and they published these results on arXiv in May of 2024, meaning that from December to May, roughly a 6-month period, they went from having this initial idea, conception, to actually implementing it, running it on real hardware, getting results, writing a paper, and publishing it on arXiv in 6 months. Now, I heard yesterday at a networking event that the average time for a quantum POC is 2 years. Now, we can actually help you reduce that time frame. We can enable you to achieve good results on quantum hardware the first time around running it. And that can actually simplify and shorten your process to validating your quantum POC and enable you to get good results, move on to the next experiment, and continuously validate whether these types of use cases will be valuable to your business moving forward. Actually, one thing that I'm excited about is that Q-Control is not one of the authors on this study. Happy to be presenting it, but we actually did not see the circuits. We didn't advise on what the circuit should look like, and we didn't construct the actual implementation to work well with our error suppression. In fact, SoftBank simply used our error suppression package out of the box, ran things, and got these results. So we're really happy that we're starting to build tools and the ecosystem is starting to have the software tooling in place for people to simply use things out of the box, off the shelf, out of the box, and get good results on quantum hardware. And so don't wait. You can accelerate your quantum applications using Q-Control software today. Come and talk to us at our booth and scan this QR code to simply go ahead and get started. Thank you.
Thank you. Questions? Yes. Maybe I should give you.
Hello. Thanks a lot for the very insightful talk. I just wanted to ask about the methods you guys have for getting better results on IBM hardware. Do you have a workflow or a pipeline where you constantly kind of benchmark against the native IBM ways of doing error suppression and optimization? Or basically, is there a way to look at the comparison of using FireOpal versus not using FireOpal?
Yeah, that's an excellent question. We do have on our documentation a page where we are consistently updating and publishing our benchmarks on the latest IBM quantum hardware platforms. And as we're adding additional hardware providers in FireOpal in the upcoming year, we'll also benchmark against these devices as well. FireOpal is hardware agnostic, so you can use it across different backends. And we're happy to say that IBM and other hardware providers are continuously pushing better performance, and we're simply helping users to access that performance at greater scale and push those systems even further. So, thank you for the question.
Thank you.